So, we are going to start, pessoal, pá. Do exercício com esta coluna não dá para mais. We are going to carry on our Vaivém Institute meeting with a presentation from our dear colleague in Istanbul. I'm you. You are in Istanbul now?
Yes, no, right now I'm in Istanbul.
With Serkut, and he's going to make a presentation about MCM. Please, it's your time. You can start.
All right. Like I have a presentation that it's actually shows a difference and the similarities between motor circuit analysis and versus the vibration analysis. So this is the topic of the review. So just like starting, we made it in the Johannesburg in the South America. Just let me, yeah.
You didn't share your presentation.
Okay. No. Can I share my screen now?
Yeah.
You can see it right here.
Now we have it. Thank you.
Yeah. All right. So with that, we made this with Mobius in South Africa. So like the basic part is that this differences between motors current signature analysis versus the vibration analysis. So we have two different case studies that we will get into, and how it works actually. Starting with, I will explain you that how the Artesis system, how model-based fault detection system is actually works. So with this, the model-based fault detection by from the Artesis is unique in its field, is actually, and the advanced algorithm used product actually, and were originally developed under NASA, is actually with the founder of us. And with that, the initial applications were the space shuttle engines and the helicopter engines. So, and after that, yes.
Talk a little bit louder, please. A little
loud. Okay. All right. And the actually the ISO norm 20,958 it sets out the guidelines for this. So all the standards are as being there, and we were the like the founder of that the standards in that sense. So, and this is applicable to the three-phase induction motors, and Artesis technology is also recognized and included in the ISO standards from there. And after from 1999, we are still developing this model-based voltage and current system, and we have device is called EMCM, so motor condition monitor device. So it's like Artesis uses a mathematical model, which is like we created during the learning period, what we call, and we call it in these days, especially digital twin. So and after that, we subtract from the real asset and from our digital twin, and what we left is just the anomalies. So, and that's how we find the anomaly detection, because normally, if you don't have any sort of faults, you would expect the digital twin and the real asset to be the same. But of course, in time, with wear and tear, you will start to have differences in the signals, in the current and the voltage signals, and especially the current side. And with that, with algorithm detection, we are just finding the pinpointing some of the really important faults. And yeah, so how it works, it's that how we create the digital twin and what mechanics we're using it, what sort of physics is that. Once we look at the three-phase AC motor and the driven asset, we do take all of it as a system. So we create something like a transfer function. So this transfer function being that and we take input voltage as an input and the output as a current. So just in the basic parts that it's like we're taking like in dx as an input and we have a transfer function based on that, and we will expect current as an output. So what we do is that since with creating the mathematical model is that with a certain input voltage, we can anticipate and we can estimate what would be the current look like at the end. And this is actually gives us a very important point, is that because that it's just once you know the current output, yeah, if you compare with the physical asset, if you just make a simple subtraction in that case, you will get something called residual current. And this residual current is actually states just the anomalies. So this here, this is our digital twin, that it's and the current is calculated based on the voltage input, based on the voltage waveform. And after that, it's and this once we subtract from the physical asset, so we are measuring the physical asset itself, and once we subtract those, and we will only get a signal that is composed only by the anomalies. So we can say that we are applying a perfect filter, like on the signal, for unique to that asset. So after that, all the changes you will get and detect will be correlated with some sort of anomaly, because otherwise you wouldn't expect any sort of anomaly at the end. So here, as you can see that in the currents in the physical asset measured, you will see some peaks on the around the line frequency, which is the 50 hertz in that case. So once you subtract and of course amplify to read in a understandable manner, so you will get to see these peaks, and after that we analyze those frequency peaks and we will find the anomalies based on that. So for the mechanical parts, it's that and of course we do check the air gap, but even that with this air gap change, we are still modeling air gap change based on that. So still, once we see any change in the air gap, we can understand it's the frequency of that change, because it will affect the current in the rotor and it will cause some distortions in the current. So, and that's how we can differentiate different faults. For example, if you have a loose foundation, that this rotor will still turn, but the the air gap change will be very different, because you will expect to see in almost everywhere. But for example, if you have alignment cases, the alignment change, the air gap change in the alignment will be much different than the loose foundation. So, and their effects on the current will be different as well. So, and just if I come back to this place, so of course, the quality of the incoming electrical supply is also important. But since we also measure and monitor the incoming voltage as well, It means that if you have any sort of distortions in the incoming line, we will eliminate it and we will filter it by the end, because we will see like, for example, the voltage signal, the blue one, and we'll expect to see similar distortions in the current as well. So by measuring the both will give us a power to eliminate those effects. So that even if you have distortions coming from the outside as an external source, you can eliminate it. Plus, you can find those faults that is caused by the external source, and you can say, okay, I need to look the external side of the asset. For example, if you are connected to a VFD, I should check the VFD, or maybe there's a coupling case, like a capacitive problem then. Or you can check for the terminals, or maybe there's a cabling issue, like there's a problem with the phases. So it gives this power. And of course, in the mechanical faults will be seen muchly in the current, waveforms. It will create distortions in the current waveforms, and as well you will see it in the third, fifth, and the seventh harmonics. So it's not just because it will not just have an effect on just one harmonic. You will see a pattern of that, which I will show you in the upcoming slide. So as you know from the vibration analysis, that the residual signal is first converted using FFT, but we don't stop there. We took it into a bit further to what we call, and what is called, it's power spectral density, the PSD. It's just to open it, it's the square, in some sense, it's a square of the FFT, and putting some more algorithm to it, which it gives not just only the frequency of that peaks. While analyzing, we can also detect and understand the power of that peaks, because once you are actually squaring it. So it's like some of the peaks will be seen much higher, and we have to normalize it, but still to understanding the strength of the peaks, it's much better on the PSD for especially in the electrical signature analysis we do. All right, after that, this PSD we compare to our ideal fleet database, which has around 1 million AC motor database, to set the threshold levels, because some thresholds are like higher in that sense, and some of them should be lower, and we create this fleet like a normal database. So, and with that, after the comparison, we'll give warning into that, or even send an email alert. So yeah, this just shows on the right hand side an exaggerated view of the bearing defect. Like the air gap changes actually here, very obvious. And in the status report, what Artesis does is that showing all the faults in a very simplistic way, that only simple bar chart, that you don't need to make very further time-consuming analysis, that this automatic fault diagnostic system is detect the faults and translate it into the 2D simple bar chart that's showing with the simple traffic lights, the yellow and red, and those are the parameters. This is taken from one of the devices called AMT. So, and it's that we are assigned the parameters, some of the faults like loose foundation, or loose component as a one parameter, and the unbalance and the misalignment being a transmission element. So it's the element that is not the motor, it's the driven equipment, or the motor, after the motor. So it could be a transmission or the driven asset like pump or fan or gearbox or all sorts of asset. And fourth being the bearing. And after that, it's more likely the electrical parameters like rotor and the stator, and other being some of the process faults like cavitation and turbulence and some gearbox issues. So we can detect all sorts of being electrical and mechanical, and we can translate it into 2D bar chart. But of course that we have a case studies, but and of course all these bar charts are coming from a raw signal that I show you, like a residual signal, and we also share that and we with the users, and you can just check manually, which helps you in some cases I will show you right now. So it's like we have a conveyor belt that's like both has vibration and motor current signature analysis, the Artesis. So the conveyor belts are suited at like a coastal port, so it's more like a transport, and for coal and the chrome. And this train is a motor, gearbox, and the pulley, main drive pulley. So it's also we monitor the pulley as well, and these are all in the 400 volts. So for motor current signatures, we have of course, we use AMT Pro, a portable device that also Carlos has it with him. Maybe he brought it with him. So it's a tester machine, just a portable device. It allows you to make a test in 7 minutes to analyze the asset and give you instantaneous report. And for the vibration analysis, using Allen Bradley Ampeg 2500 with a monitor analytical software. So it's a motor with 1480 RPM, and you see the gearbox ratios is 30, and the pulleys, and we saw the pulley A and the bearing of it. And this first we made it in the April here, and the amplitude is related to rotor around the main line frequency, which is the 50 hertz here, being also, and there is a current imbalance of 15% in the equipment. So, which means that the difference between the phases was more than 15%. So this shows a clear fault, first of all, that you shouldn't expect that, like without even looking anything. So up like above 5% of the current imbalance is mainly indication of faults, that it's could be rotor related or stator related. But the electrical related faults, maybe in the minor sense, could be like a terminal or this sort of fault, but it's mainly related to the stator. So, and coupled with a running around like 80% load and has some unwanted vibration and the falls over time in the long term. So, and vibration test, we made this, this distributor made this test, not us. That they confirmed the motor current signatures result on a vibration. The rotor faults are indicated by, of course, the rotor bar pass frequency surrounded at the side bands of 6,000 CPM, which is like 2 times the line frequency at that time. So, and this is, and after the July, this is the 25th April. So we see this mechanical faults here, as like if you, how would you say that, like to find it? It's the it's because it surpasses the green area, because normally this as I was telling you earlier, that this blue line is our signal, what we get from the signature analysis and and through modeling. And if it's under this green area, it means that the motor is working in the normal condition. And this green and the red area is based on our fleet model, as I told you earlier. So these two, we have a false indicating that, which happens around the line frequency, shows a trouble. So, and after that, it's the vibration test actually confirmed that. And after that, the maintenance overhaul this decrease in the amplitudes in the vibration. And after that, it's the amplitude change significantly after the maintenance in September. And yeah, so here, 1 second, it's the how we so yeah, and after that we check for imbalance, looseness, and misalignment is on the vibration spectrum. So looseness, imbalance is shown actually high amplitude peak at running speed frequency. So it shows still the around the line frequency, but plus and minus of the frequency. So just let me show you this. So this is our chart that used for the fault patterns that are automatic diagnostics, as well as follow these patterns. For example, an alignment cases, it's frequency line plus and minus the shaft frequency, so the turning frequency of the rotor, and we were expect to see at the third and fifth and seventh harmonics. So, and for misalignment angular, we will expect it to see just at the one side of that peak. So, and these are all actually based on the mathematical models like vibration analysis, like for example bearing and rotor and BPFO and rotor bar crack, rotor bar, and even the stator turn to turn or coil to coil faults. So which that and looseness is shows at running speed at the beginning of the PSD spectrum, so at the low frequency ranges. So while here vibration reading taking shows a dominant here, as you see at the RPM with the harmonics, it has some small harmonics there, and this is the motor. Here it is. So, and we indicated that here the same a rotor problem, because it's indicated sidebands around the line frequencies, as if in here just as if here. So in the around the pole pass frequencies, we indicated that. And just let me here. So and this is actually in the we show that there is a concern on the rotor, and we made the reporting. And on a vibration spectrum, this is indicated by a peak at rotor bar pass frequency, this. But vibration reading taken on the 8th August indicate that these frequencies are present, but at the low amplitude. And they say it does not indicate a concern. And after that is the same asset. Reading at like 28 September shows a slight increase in the amplitude, but still not to concerning levels. And vibration reading taken on 4 April, that just a month ago, increase in the amplitude of 50% or more. So it is the normally that you would just a very quick increase. So and after that, okay, you say the vibration analysis shows a very slight increase in that sense. You would normally you would say, okay, there is nothing to worry about to the customer, to the user for a vibration analysis expert, but and after you will see with the rotor problem a sudden increase. So with that, it is actually gives a bit challenging on that point for vibration analysis, especially on the rotor side. So it's a motor current signature analysis like that is using for the rotor bar analysis, especially. It's a very early indication of those faults, and some alignment issue that this find has in the limitation on some parts, but working together provide a much better predictive maintenance solution overall. So, and because you will have a chance to complete each other, because some of the, as I just showed you earlier, some of the faults, especially on that side, could be very problematic to find by vibration analysis, unlike traditional electrical signature analysis. So this using the both and checking and making cross-referencing and justifying gives you much better reliability option in that sense, just for the users. All right. So yeah, it is actually for me, it's the end of the
Okay, thank you.
Seminar. Do you have any questions about it or any general question?
At least I have. Perguntas, pessoal. Alguém tem perguntas? Eu tenho perguntas. Could you there is here several persons that came from power generators, generating industry. What is the capability of this technique? Could you explain a little bit the capabilities of MCM for generators, alternators, I mean?
Yes, for we have a device like for power industry. We have another device. It is called EPCM, and it's mainly used for the generators and the wind turbines. And of course, it's mean that we work it with the synchronous motors in that sense, with the EPCM. And it can be used for this type of generators, and for and also that for the pumps or the fans or the other assets in other critical assets in the power monitoring, we can use EMCM as it's shown here in the slide.
Okay, and for hydro generators rotating at very small RPM, is it possible to use that?
Yes, but for that we need to have a bit more information about it. Yes, it is. We have hydro generators in applications. We made it. So for electrical parts, for electrical sense, to finding the electrical faults like rotor, stator, currents, balances, to monitoring in that sense, it's quite. We gave every parameter, but for the mechanical parts, we have to check for the generator type. So if you could like provide me the generator data sheet, that for us to actually check and offer you the correct solution in that sense.
Okay. Another question. What is the importance of energy monitoring on the return of the investment in MCM?
Oh yes, thank you for asking that actually. So like the main issue with also that to having an electrical signature analysis device is that it also allows you to make manipulation or calculation on the electrical side, which is the most important part, is the energy. So since we can understand and we know the faults, and also we track the energy at the same time, so we can make a comparison. We can give you, and you can have the report that based on your inefficiency, based on your fault. So for example, if you have a bearing fault and some minor alignment issue on the asset, and you need to work, you need to keep, you cannot stop the machine until 2 months, for example, and or you are waiting for a part, and in this case, you will start to lose, like for example, about a 3%, 3.5 based on the fault as an energy inefficiency. So and you will get, but with the vibration monitoring or the other type of devices, you wouldn't actually see that, and you wouldn't see your loss, and also you wouldn't express to the management, to your team, that how much energy you're losing in the time. But with the electrical signature analysis, and also of course with the Artesis, that you can see that and all the effects, and you can see all the effects on the energy, which also, if you have multiple assets, and you can gather all their data, and you can just present a report that you're losing yearly like $15,000 or $50,000 just on inefficiencies that is caused by the fault. So, and you only need maybe like 40,000 euro to fix all the problems, and maybe just 10,000 euro of overtime, but to fix all of this and to make a better maintenance, better performance overall.
Okay, thank you a lot.
You're welcome.
Mais questões? I'm recording your presentation, but people is asking if they can have your presentation.
Yes, I will send to you. Okay, and you can share with everyone.
Okay, so if there are no more questions, and we are already a little bit late, I'm going to thank you a lot for your presentation. It was really interesting and a great presentation.
Yeah, thank you so much, and thank you all for participating and listening to me. So, and if you have any questions, just to want to learn how it works and just to learn more about it, electrical signature analysis, how Artesis works, you can always contact with Carlos and us, and we will provide you more details about it.
Okay, thank you.
Thank you. Have a nice day, everyone.
Have a nice day. Bye.
Bye.